spring where it is been subjected to compressive force. All of you can see here the compressive force here, A. And under the action of this force A, I am naming it A as your force, compressive force. This spring will have the deformation. It will be compressed, so there will be deflection. Let us call it D. So A and D, A is the force and D is the deflection. Action and deflection equation, as I told you, we need relation between these two. So this is the simplest example. When we relate these two, we bring the concept of flexibility and stiffness. So everyone knows about spring stiffness equation. F is equal to minus kx. All of you have heard this. K is the spring constant, x is the deflection, and F is the force. So here this equation is written on the right hand side in a similar way. You know, the spring constant is, let's say, S. F is equal to, this is your force A is equal to SD. D is your deflection. So this is the very simple spring stiffness equation. I can define the constant S. This is the stiffness. We call it, at that time we call it stiffness. In now we are going to analyze beams also. There also we are bringing concept of, because spring is elastic and we are also assuming all structures elastic. In your solid mechanics course, you have draw the linear curve of elasticity limit. We are not going ultimate limit. We are going to analyze the structure which are behave linear with the force and deflection, stress and strain. The stress and strain curve is linear, so linearly elastic material. You have tested the material, you have done the tensile test, all those kind of tests you have learned. So testing, basically, whatever testing you are doing is linear, and we still follow the Hooke's law. So linear meaning, if we have the linear elastic spring, we can analog this concept to the continuous beam or any kind of beam or any kind of elastic structure. So we assume beams material also behave elastic, because when you remove the load, the structure will regain its original position. When you apply the load, structure will deform, but when you remove the load, it will come to its original position. Similarly here, when you remove the load of the spring which you have compressed, it will come to its original position. And similar thing will happen with the beam also. And because of the elastic behavior of the spring and the structures, we are bringing out the concept of stiffness as well as the flexibility. So we can define, this is a spring equation. A is equal to force is equal to minus kx. You can correlate this. Only thing is I have defined the different symbol here. A is equal to SD, where S is the stiffness of the spring. It is defined as the action required to produce a unit deflection. Now, what is the definition? If I can write S is equal to A by D. S is equal to A by D. When you make D is equal to 1, you can have stiffness. So definition, if somebody asks you the definition of the stiffness of the spring is defined as the action required to this is the action required to produce the unit deflection. If you make D is equal to 1, naturally S becomes force. So it is nothing, stiffness is nothing but the force or the moment. It can be moment also. When you go further for analysis of the beams, it can be moment also. So when you want to write the moment equation, we can write something like, moment is equal to S is the stiffness, and then this is D is actually, I can say in moment it is theta. All of you have seen this equation 4 EI by L, and we will see this equation 4 EI by L. All of you know that for EI by L. You have used it in slope deflection and moment distribution method. We will see when we are talking about beams, M is equal to S theta. Where the variables moment I talk about theta, where variable force I talk about deflection, but the stiffness is something which relates the force and the deflection, where it is a force produced because of the unit displacement. If you make D is equal to 1, you can get the force which is nothing but the stiffness. Now flexibility is something which is opposite of the stiffness. F is equal to 1 by S. It is the reverse. So if you can substitute, flexibility of the spring is defined by the displacement produced by the unit value of the action A. So reverse. So instead of deflection making unit, I can make the unit force. If you apply the unit force, you get the flexibility. And this is equation is written in a reverse order. Reverse. Here you can see the left hand side the force. Here you can see the left hand side the deflection. And both are useful. In stiffness method, we are going to have on the left hand side the forces. And on the right hand side, we are having deflections, and we are relating with the stiffness matrix, actually, stiffness matrix. And in flexibility matrices, we are going to write the deflections on the left hand side, and we are going to write the forces on the right hand side. And these are going to relate with the flexibility matrices. And when we talk about general system, so all of you, I want you to understand the basic definition of stiffness and the flexibility. Flexibility is nothing but it is the displacement. It is displacement. If someone asks what is flexibility, it is actually displacement produced because of the unit value of the force. And as I told you, you can like this is the equation of the symbol and inverse equation and all. So unit of flexibility is unit length per force. Stiffness has units of the force per unit length, actually force per length. So let us go to now the next slide, where we will be discussing more generalized concept of this stiffness and flexibility coefficients. So we are going more general about this concept. The first diagram you can see, where now spring, forget out spring, because spring is just spring also appears everywhere in the structure, somewhere in the structure where spring supports are there, or there are two truss actually loaded members where they are connected with the springs. Anything you can see in the real structure also. So whatever basic concept when you want to understand, you start with spring, and then axially loaded bars, then trusses, and then beams. Beams, of course, are bending members, so behavior is more complex as compared to spring, but we are using the same concept. As I told you, it is a elastic spring, but we are also considering our beam, which is elastic, linearly elastic beam behaves, the material of the beam behaves with the Hooke's law, it is elastic, and we can bring out the concept of stiffness and flexibility, which we have used in the spring for analyzing the beam also. So what we can do here is, you can see here the concentrated load applied, the beam deflects. So if you want to define the stiffness and flexibility of this beam, this is single load, simple support, single structure, okay? So when you apply the unit force, what will happen? It will deflect under unit load, and what are deflection? I am calling it flexibility. So how to generate the flexibility coefficients in the beam? By applying unit applied force. So the famous equation for deflection of the simply support center deflection of the simply supported beam is I would say delta deflection delta is equal to PL cube by 48 EI. PL cube by original equation is PL cube by 48 EI. So when you make P is equal to 1, you get deflection. Here, I only thing is I have not added here. What you can do is okay. What you can do is sorry. Here, sorry. Here you can write P. Some problem. No problem. I hope all of you are able to understand. What I'm trying to say, our original equation is PL cube by 48 EI. When you make P is equal to 1, when you make P is equal to 1, you get flexibility. Because flexibility is nothing but the deflection because of unit applied load. So here when you make A is equal to 1, you get deflection. So flexibility coefficient for this beam is L cube by 48. So you can be asked individually in multi-choice questions, and I have seen in entrance examination also. They usually ask, a simple thing like, okay, calculate flexibility coefficient for this beam. You should be able to get this answer. Similarly, stiffness, which is opposite, I know the equation PL cube by 48 EI. Stiffness is a force because of the unit applied deflection. So here, if delta is equal to PL cube by 48 EI, when you make delta is equal to 1, when you make delta is equal to 1, you want to calculate the force that is nothing but the stiffness. So the reverse equation of this, what is, if PL cube by 48 EI, P you can make the left hand side, that is delta is equal to 1. If you make the left hand side 1, you get the force. And that force is nothing but 48 EI by L cube. It's the opposite. Both are opposite. You can check here. Both are opposite. So this is for the simple beam. All of you know the definition, how to calculate the stiffness coefficient, how to calculate the flexibility coefficient. When we solve the more realistic examples, we will come to know, okay, what are the things. Now go to the more general case. So you can see the right hand side figure here. The more general case here, where several loads are applied. A1, A2, moment is also applied, and there are several supports. So now the question is, how do we relate the stiffness of the force and the deflections through the stiffness and flexibility coefficients? There will be so many, there will be 9 coefficients generated. There will be 9 stiffness and flexibility coefficients, and we will see how it can be generated. So what you can see here is this is a beam where 3 loads are applied. Deflected shape of the beams I have shown. And assuming, of course, this is, I told you the joint and supports are only deformation. It just for the concept purpose, I have shown the deflection here somewhere in the middle of the span. A1 may cause D1. Please mind A2 may also cause D1. And at the same time, A3 may also cause D1. Similarly, deflected profile, you can see D2, which is the deflection, which can be caused by A1, A2, A3. And the rotation at last support, D3, which can be caused by A1, A2, A3. There we have to now bring the concept of superposition. We have to bring the concept of stiffness.